The search for dark matter continues, and astronomers and particle physicists are working separately and together to try to figure out any way of detecting the presence of dark matter in the universe. At the largest scales, we see gravitational lensing. We see how galaxies move around, how galaxies can be stripped of their dark matter compared to other galaxies. There are many possible explanations for dark matter. One is that it is particles, and one specific version of that is that it is heavy, slow-moving particles that can accumulate inside various objects in the universe. And if it is these WIMPs, then it could be possible to detect their presence, not necessarily directly, but indirectly, by the neutrinos that they emit as they annihilate with each other in concentrated areas, like say at the center of the Earth. So my guest today is Dr. Giovanni Renzi. He is a PhD physicist from the Free University of Brussels, the Université Libre de Bruxelles. And he is a member of the IceCube collaboration, specifically a group that works on interesting exotic ideas of detection with the IceCube Observatory. And he has completed a 10-year search for excess neutrinos coming from the center of the Earth that could be caused by annihilating dark matter. All right, enjoy this conversation with Giovanni Renzi. Giovanni, why did you and your team think that it would be just possible to detect dark matter using the IceCube neutrino detector?
So the first point is neutrinos are the only particle which can get through the Earth, for example, or through very heavy environments like exploding stars, etc. So we have plenty of possibilities that open up when we think about using neutrinos. And in this particular case, we started from the fact that there could be dark matter accumulating in the center of the planet. Yeah, neutrinos are the only particles which can get to the surface, and so we can detect them and see dark matter in this indirect way. So we're not saying dark matter itself, but the byproducts of dark matter interacting.
And I know there's been a lot of this research in the last couple of years, like mostly thought experiments and things like that. I think Rebecca Lean is doing, I've interviewed her in the past, a lot of people doing a lot of work of this idea that if there is dark matter that is coalescing inside objects like the Earth or the Sun or Jupiter or whatever, that one way to detect that would be that there would be this excess heat that is coming off of the planet or the sun or whatever, so is that sort of excess heat connected to this idea that it would also potentially be producing neutrinos that would then be detectable by IceCube?
So the point is, neutrinos bring energy out of the bodies, celestial bodies. We know, for example, supernovas, they implode because neutrinos are bringing all the energy out and they cannot hold anymore. I don't think we can connect it really with the excess heat, but we can see what's going out of the center of these celestial bodies, and this can be where dark matter is hiding. Well, one of the places, and especially it's interesting because it's in the solar system, it's close, and it's much easier to see something close than far away. We have analysis even for the center of the galaxy, but yeah, there's much more dark matter there, but it's also much farther away.
Now, there are plenty of other experiments that are attempting to directly detect dark matter here on Earth. Lots of laboratory experiments, old salt mines, nickel mines, things like that around the world. But then also there are the indirect methods of detecting dark matter using telescopes. How does sort of what you're doing compare to a lot of these other efforts, and where does it overlap?
So our analysis is indirect dark matter search, because we're observing neutrinos and we're not observing dark matter directly. But the point is that indirect and direct dark matter searches are kind of complementary. We can detect, since they are accumulating in the center of the Earth, it means that there are slow dark matter particles, because the fast ones don't get trapped. While when you're searching with that direct search, you need very fast particles, because you need the most possible energy to see some effect. So it's kind of complementary. Yes, so that's why it's interesting, even if our results are not really comparable in terms of limits that we can put, but we are really searching the two different sides, the two opposite sides of the speed distribution.
You mentioned this sort of idea, this differentiation between the heavier, slow-moving particles that are able to sink into the Earth and actually sort of remain inside, that could then generate the neutrinos, versus the potentially the fast-moving particles. And I know, like, a lot of dark matter scientists say it's entirely possible that dark matter is actually a whole bunch of things all happening at the same time. It's this, it's that, it's primordial black holes, it's all these things together. But like physically, when you set up your experiment and you're looking for certain kinds of neutrinos, what sort of physical interaction do you imagine is happening inside the Earth with these heavier dark matter particles?
In many cases, we can think of dark matter particles annihilating one onto another, and this can produce like visible matter, common matter, let's say. And so what we are observing, what we want to observe with IceCube, what we wanted to do is, since neutrinos can be or direct product of this dark matter annihilation, or secondary products of other particles interacting after dark matter annihilation, neutrinos are the only ones who can get to the surface. So the basic idea is that dark matter is accumulated in the center of the Earth, and since there's some density in this particular place, the dark matter particles can start to annihilate.
Right. And I guess that sort of leads back into what I mentioned earlier. Like, there could be other effects, like excess temperature coming from the Earth, again, coming from potentially these particles annihilating. But the only thing that can reach your sensors are the neutrinos, and so that's what you're looking for.
Yes, the other particles are going to be stopped by the Earth itself, because there's matter. So the other particles are not transparent to the Earth.
So give us a sense of the sensitivity that would be required to find these neutrinos, and at the same time, you've got all the neutrinos coming from the sun, you've got all the neutrinos coming from supernova, and just in general from all out there in the universe.
So in terms of numbers, when we get to the final stage of our data selection for this analysis in particular, we can expect like maybe 2 or 3 or 5, not much more. This selection is very strict. I mean, we try to remove everything, and we're watching a very precise direction, which is the center of the Earth. So we cut off all the rest of the sky, let's say. So yes, we can expect a bunch of events, not more.
I mean, when I think about the orientation of IceCube, it's like down at the South Pole.
Yep.
And the sun is going to be perpendicular to IceCube. And so all the solar neutrinos that are streamed by, they're going to be coming from the wrong direction, and you can just kind of throw those out. But then you've got all of the neutrinos that are coming from around the entire universe coming at us from all potential directions. And so you're looking for like a statistical increase in coming from the center of the Earth towards the detector.
Yes.
And And I mean, does a bunch, 10, whatever, does that beat then the average number of particles that come from general directions?
Yeah, the most difficult part of the analysis, I think, was reducing the background, because for our case, actually, for example, astrophysical neutrinos that are like the main analysis for IceCube, for us it was background, even the astrophysical neutrinos, but reducing the field we observe, so we really just look down for this analysis, because we are not interested in what comes from all the other directions. What we have is, astrophysical neutrinos. We have also neutrinos that are produced in the atmosphere on the other side of the Earth, and which can go through the entire body of the Earth, and that's all. Basically, we don't really see other things. Sometimes we can have some events that are very vertical and which are coming from up, but since they're very fast, sometimes the reconstruction is wrong, and so we see them like going from the center, but instead they're coming the exact opposite direction. But the most difficult part was reducing the background, because we really needed, since we expect only a few events from dark matter. We needed to reduce at the real minimum the number of events we were using.
Right, and I mean, you identified that in the paper that the atmospheric neutrinos produced by events happening in the atmosphere was one of the biggest sources of potential noise in this program. And so, I mean, I guess you don't know what a dark matter neutrino looks like, and so when you're just seeing random neutrinos coming through, potentially produced in the atmosphere at the North Pole, it's hard to know. So, I mean, did you have some approach where you're like, okay, we know what atmospheric neutrinos look like?
So the point is, we cannot identify if a neutrino comes from one thing or another, because neutrinos are always neutrinos and they're not different if they come from dark matter or from the atmosphere. But the point was to analyze, to find an excess. So let's say from simulations, we expect a certain number of events, and we can. So what we tried was to observe an excess. Let's say to count more neutrinos than we expect with only backgrounds. So this was the idea. So we cannot identify which neutrino comes from where, but we can find if there are more neutrinos than expected.
Right. And it sort of makes me think about that incredible image from IceCube of the Milky Way, purely because there's an excess of neutrinos coming from the disk of the Milky Way. And so you can see the core and the spiral arms.
It's wonderful.
And it's amazing, right? Like one of the greatest pictures ever taken by pictures ever taken by IceCube, and that is that you're identifying excesses of neutrinos coming from various locations. And the sun is obviously this giant neutrino producing ball. So now you did two kinds of searches, though. You did like a high energy search and a low energy search. Can you explain sort of what you were looking for between those two searches?
So we started with one analysis, but then at a certain point we had to split, because in IceCube, when we see high energy events, and I'm talking like more than 1000 GeV, for example, we can see muons. They're very long tracks, and it's very easy to identify, and the muons basically bring almost all the energy from the neutrino that generated it. While when we are at low energy, the muons have a shorter tracks, and this kind of mix up with the rest of the particles that are produced in the interaction, and what we see is kind of a ball of light. So we have to observe different things when we are at low energies. Also, finding the reconstructing the direction of the original neutrino is more difficult because you have a lot of things going on in a smaller space, while when the energy is higher, we can see clearer. Yeah.
Now, people who are listening or watching this interview are going to be like, "You're burying the lead here. Did you find dark matter or not?" And obviously, you would be holding your Nobel Prize with you while you were conducting this interview if you actually had found clear evidence for dark matter. So, what did you find, or what didn't you find?
We didn't find clearly dark matter, and in the field of dark matter, everyone is really shrinking the space where we can find dark matter. And when I'm talking about space, I'm talking about phase space. I mean, more like the possibilities of where we can find dark matter, or how dark matter can be, are shrinking because we are testing everything and we don't see it yet. Each time we do an analysis, we can push the limits. So that's what we did. So you can say like we can get down to this limit, and down to where we don't see dark matter, and that's what we claim in the paper.
Now, obviously, they didn't find the excess neutrinos coming from the center of the Earth that they were hoping for. It would have been Nobel Prizes all around. He didn't appear to be holding a Nobel Prize, until we have to assume they didn't find it. And that is called a null result, that you are searching for something, you don't find it, that a null result is still a result and you should still publish it. And yet, researchers are incentivized to not publish their null results, or to not go and look for these kinds of things. You want to try to find results. You want to try to be able to prove theories, as opposed to necessarily find a lack of evidence for a given theory. And yet it is as important as the alternative. And so I had a much longer conversation with Giovanni about what it's like to be searching for null results. What are the implications of those? How can we incentivize null results to be seen and to be searched for by scientists? Now, that longer conversation is over on Patreon. It is available free. You don't have to become a paid member. You just have to follow us on Patreon and you can access that. So back to the experiment. So, you ran this result. You didn't detect the bunch of neutrinos, the excess of neutrinos that were coming from the core of the Earth. When you think about the other indirect methods and sort of setting those sort of limits, when you think about, say, maybe some of the astrophysical searches and things like that, does it, if an astrophysicist came to you and said, okay, we're going to do a giant survey now of the universe to look for dark matter again, do you have any tips on where we should and shouldn't look? Would you give them any suggestions on how they could narrow their search from an astrophysical perspective?
So for indirect searches, I think the best is like focusing on places where we can expect something. And so, for example, the center of the galaxy is probably the most promising source, because we know dark matter is there. If dark matter exists, it must be there. And also, if we observe the center of the galaxy, we are not constrained by neutrinos, because we can observe other things, like, for example, photons, light, just excesses of light, for example. So I'd say for this type of indirect searches and this model of dark matter, which is the main model which has been tested in the in the recent years, the center of the galaxy is the most promising source.
Right. And I see what you mean, that inside the Earth, you've got the material of the Earth that's blocking all of those photons. But if you're going to make your observations out there in the universe, then you can see both the neutrino flux and the photon flux, and hopefully see some kind of connection between them.
Yeah.
But that's different than potentially, say, measuring gravitational lensing and using that as a way to observe, or watching as, I don't know, satellite galaxies are orbiting around the Milky Way and using that as a way to kind of probe so, I mean, do you think about that, any sort of indirect gravitationally lensing methodologies?
So the point is, with gravitational lensing, we can see where dark matter is, but we cannot say anything about what it is. And with testing particles means that we are testing some hypothesis on what dark matter is. And that's where I see as a difference. And in terms of neutrinos, since we can detect, you can imagine if we need a cubic kilometer detector to detect neutrinos, and so it's difficult to detect neutrinos. So the farther we go, the smaller the chance. And for example, in some cases, we combined with other experiments like gravitational waves experiments or telescopes, normal telescopes, let's say. So because, for example, we could see one neutrino or two neutrinos from a certain source, and so we send alerts to the others to see if they can see anything coming from that point of the sky. It's one of the goals of the coming years for IceCube, to kind of start finding the sources of neutrinos. So the farther we go, the more difficult it is.
But when you think about, say, the amount of dark matter that might be inside the core of the Earth, it's probably not a lot, but I guess it's close enough and it's dense enough that it's starting to interact and produce potentially neutrinos. When you compare that to the amount and density of dark matter there might be at the center of the Milky Way, it's going to be dramatically more, but farther away. And so, the inverse square, I guess, is going to be sending less of them in our general direction. But when you think about out there in the universe, that even the amount that's in the Milky Way is just a tiny fraction compared to trillions of solar masses accumulated into these enormous quantities. And so does that kind of get back to what you're talking about how,
yes, I think it's easier to see an excess if we observe a particular object or a particular direction of the sky, than to see like an overall excess of something all over the universe, it's easier to spot something if you look at something in particular than spot something all over the universe.
Yeah, I think about, say, some of these searches for dark matter where they've found, say, galaxies that have no stars and gas, but a large amount of dark matter. And then the alternative, where you have galaxies with a lot of stars and gas, but no dark matter. And, some process has separated these things out. And so in theory, these should be giving off a different neutrino signal if you've got self-annihilating dark matter, but it's just, they're so far away. You're going to get,
exactly. Yeah.
A bunch will seem like a lot.
Yeah.
Right.
Yeah.
One. And so, you talked about sort of the changes that may be coming to IceCube. The plan is to go from a 1 kilometer cubic version. Gen 2 takes us up to 10 cubic kilometers?
Something like this. Yeah.
With sort of different levels of resolution at different parts of the detector. So, if you were to then come back around and go, okay, Gen 2 is ready to go, you've got another 10-year search beginning. How would you sort of adapt to using that new instrument?
So from the point of view of dark matter, 10 cubic kilometers means we can aim at higher energies. I think the center of the Milky Way can still be a promising source. From the point of view of ice cube in general, what Gen 2 is thought for finally finding the sources of neutrinos. And so if we have more precision in reconstructing the directions and the energy, we can really point the sources, which is a thing we are not really able to do right now.
I mean, and so because we're relatively close to the center of the Earth, then that's where you're going to get the most particles. I sort of think about the Event Horizon Telescope, and they really can only take 2 images of supermassive black holes, M87 and the heart of the Milky Way, because they are roughly the same size in the sky. And then anything farther smaller is sort of beyond the detection limits of this specific instrument. Yep. And so with Gen 2, like, what comes online? Does the Jupiter come online? Or is it, or would the center of the Milky Way be a brighter source for neutrinos than Jupiter, which is relatively close by? So
the point is that for annihilation in the planets or the sun, you need a process of accumulation of dark matter, which comes with time. And while the center of the Milky Way is a point where dark matter has always been, if we want to say it like this, it's the center of gravity of the galaxy. So dark matter is not accumulating in the center of the Milky Way; it's already there. While locally, we need to wait for the accumulations, and there was enough time to accumulate certainly in the sun, maybe Jupiter, but for the Earth, we're not yet at the maximum of this process, let's say.
Right. But I mean, obviously, trying to observe from the sun, the problem is the sun is also producing neutrinos, and so it's a difficult source to observe. So let's say we could take Ice Cube, remove it from Antarctica, and move it to anywhere in the universe, and set it up right next door to what you think is the most powerful source of annihilating dark matter. Where would you go? Would you set it up outside a black hole, or is that?
So
where would you like to put
it's
Ice
an
Cube?
Interesting question. The point is, there is a lot of background, not only neutrinos, but also other things, mainly muons, which are produced in the atmosphere. And the closer you get to the source, like, if I think of the center of the Milky Way, the more you have a lot of other particles which are interacting in the detector and producing light. And so I'm not sure that getting closer to a source like a center of the galaxy or a black hole can increase our sensitivity, because there is also a lot more background which we have to get rid of.
So I mean, do we dig a hole in the oldest neutron star in the universe, right? Because then you get age, and you also get the gravitational pull to be able to trap dark matter particles potentially inside of it.
Yeah, and also, the point is, with Earth, we have a natural shield against a lot of things, because of the Earth itself, and because of the magnetic field and other things, because of the air also. And so, I guess ideally a neutron star could be interesting. The point is, with ice cube, we use the light that is produced in the ice. So we need ice, and
Right.
I know that,
So we need a place with ice.
or water, because there are also experiments in water, like in Russia or in Europe. And the
Right.
point is, we need water because we are exploiting an effect which is called Cherenkov effect, which is the light produced by charged particles when they go at speeds that are higher than the speed of light. And I think this principle could not be applied on a neutral star. Maybe we should think of another kind of experiments and other ways to detect neutrinos at that point.
No Cherenkov radiation coming from neutrons in a neutron star being hit by neutrinos. Maybe I guess the oldest.
There certainly is some things we could do, but it's gonna be different. Yeah.
Right, but I guess I'd say the constraint is you move ice cube, so not you come up with an entirely new detector that you can then deploy anywhere in the universe. So I think that's fair.
One interesting thing is, if you multiply the number of detectors, you can cross the data and be more precise. At this point, I think we have 3 operating on Earth. And one could think like placing one on, since we need ice or water, we could think like of Europa, the Jupiter satellite, or I'm just playing with things. But
okay. So we turn Europa into a giant Cherenkov detector. We fill its entire interior, all of its water and its ice shell with detectors, and then hopefully we can detect the excess neutrinos coming from Jupiter.
Yeah, it could be
done.
All right, done. I don't know if it can be done, but it could be interesting, fascinating, certainly.
Yeah, all right. Well, we'll get that started. I'll put that into your future funding. Giovanni, what are you obsessed with right now?
So, actually, after my PhD, I left academy. So maybe I'm coming back at a certain point, because never say never. But now I'm actually a teacher in secondary school in Europe, and I really like it because I cannot talk a lot about neutrinos, but passing this knowledge and the love for physics and science to the new generations, it's a thing I really like, and I see myself in this place for a lot of time. But I repeat, never say never. Maybe I will come back for a postdoc at a certain point.
It's interesting when you sort of think about children as being natural scientists. Like often when they're young, their natural inclination is to form theories and test their hypothesis and so on, and be naturally skeptical about the kinds of things around them. And then later on, through sort of the way our mass media works and the way various politics and all that goes on, that people sort of lose that natural inclination. And so it'll be interesting to see how you get a chance to actually influence the children as they.
I really find it fascinating, like watching children doing experiments. Like, for example, when they throw things at the floor, they're really testing gravity, and they do it again and again to see if gravity always works the same. And some parents get angry because they're throwing things, but really they are just experimenting and trying to see if gravity works always the same.
Yeah, that's awesome. Well, Giovanni, thank you so much for your time. Good luck with both your new career as well as any ongoing searches for dark matter.
Yes, thank you.
I hope you enjoyed this conversation with Dr. Giovanni Renzi. Now, I'm going to give you some more interviews that we've done on related topics, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Bear Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Sean Sargent, Spiderswap.io, Stephen Farley-Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. Now, I have done, dozens of interviews with various astronomers and particle physicists about the search for dark matter in the universe, both at the larger astrophysics level, where you're searching for gravitational lensing and trying to perceive the movement and concentrations of gravity and mass out there in the universe, but also at the sort of lab level, where people are searching for dark matter in the lab with various detectors across all of the different wavelengths. The mystery continues, and I hope you're enjoying this ongoing search for dark matter as much as I am. So I've got a couple of other interviews that you can look at, but until we find out conclusively whether it exists, whether it doesn't exist, whether it's a problem with our measurements, whether it's new physics that are required, whether it's particles, whether it's black holes, the whole process is really fascinating and very enjoyable. All right, we'll see you next time.